We left off here at the end of the first lecture video, which is if you want to be more confident, you can do one of two things. And the first thing you could do is just make a larger interval. When you make a larger interval, let me put it this way. Your interval is basically saying, hey, I'm pretty sure that whatever I was looking for in the population proportion, the population parameter, is somewhere between these two numbers. You can see it's yellow here. And if you swell that interval, make it larger, higher here and lower here, then you're going to be more certain you caught it, more certain you caught whatever the true proportion really was. So that's one option. But how can we raise our confidence level but without the downside of making an interval so big that it's useless to us? And the way you can do that is use a bigger scoop, i.e. take a bigger sample, take a better sample, that kind of thing. So the problem is that somebody has to pay for everything that you do. I mean, scoops of beads is one thing, but I mean, if we remember those beads, and that is really a metaphor for something much bigger, namely calling people up and asking them who they're going to vote for in the next election, or whether they're going to give away Halloween candy this year, or what portion thinks that, I don't know, Israel should give up portions of Jerusalem to the Palestinians, this kind of thing. So if you're going to go call lots and lots of people, i.e. get a bigger scoop, you're going to have to pay somebody to do that. You got to pay for the phone lines. You got to pay for those people to be fed and to work, and you got to train them to do it right, and it's a lot of time and money. And besides that, how large is large enough? I mean, you don't want to keep spending and spending and spending time and money. You want to have a sense of how much error you want. Do you want to be 3% error? Do you want to be 4%? I mean, everybody would love, 1% error, but the problem is to get 1% error, you got to do, 3,000 people. Nobody's going to do that because you don't have that kind of time. So those are our issues with that. It's all well and good to go, well, just get a better sample. Yeah, but who's going to pay for that? You got the time to wait for that? And how large is large enough? I mean, if you want to have accuracy, i.e. margin of error that's smaller, you're going to need to go get more people. So what do statisticians really do to raise confidence? And the answer is it depends. It depends on the time and the money and the personnel that they have, the people they have to pay to do this, how trained they are. It depends on how much error they can live with, right? Can they live with, 3%? Can they live with 4%? Can they live with 5%? It all depends. It also depends on how much depends on the results. I mean, if you're trying to call people about, I don't know, whether they're going to give away Halloween candy this year, that's not as big a deal to you as who they're going to vote for in the next presidential election, right? So if it's a really big deal, like the next presidential election, or I don't know, the Jerusalem, issue for Israel and the Palestinians, then you're going to want a larger error, or a larger N to get smaller error, right? Because it's a big deal, so you want that accuracy. But if it's not a big deal, like Halloween candy, then whatever, take a smaller N and just live with the fact that you're going to have more error, which means your interval is going to be larger. You're going to have more slop factor between the two. All right. Now, suppose when you were, I don't know, magically pulling scoops from the box, the bead box, you had people next to you and they also pulled scoops. And person number one had a 30.8% plus or minus 8.3%, and the other had 18.3 plus or minus 6.9. So first thing you got to do is write that out in interval notation. So how did I get these numbers? Well, all I did was I took 30.8 plus 8.3. That gets you 39.1. And then I took 30.8 minus 8.3, and that gets you 22.5. And then I do it again over here, 18.3 plus 6.9, 18.3 minus 6.9. Now I know what you're thinking. You're thinking, Alana, why are you having us do this? Well, I just wanted to show you something. So I'm going to pull this up. This is CNN's Election Center for 2012. When I'm recording this, I'm only like a week away from the elections between Obama and Romney. So you can see here what they've got. Or maybe you can't. I'll zoom in a little bit so you can see better. Okay, so you can see that they've got these polls right here. So this is neck and neck. This is a national poll. And you can see they were 48%, 48%. Or, and by the way, they're only really reporting the stuff where they're neck and neck. It's a long story, but this particular one is only interested in the particular states that are really close, the stuff that's really close. So here's Ohio, for example, which is a battleground state. And you can see that they're saying Obama's 50%. Okay, and it sounds great. Obama's 50%, 46% for Romney, and you think, oh, then Obama's going to win that state. But be careful, because the margin of error is right down here. See it? They don't put it right up there. They don't say, oh, well, Obama's really anywhere between, 46.5 and 53.5%. They don't say that, but that's what it is. And that's why I'm having you take the time to do this right here. What they're writing on that sheet is 47, or 50%. 50% plus or minus 3.5%. That's how they write it in the news, right? Matter of fact, they don't even write that. They write 30.8% and pretend like that's all there is, right? And then you got to search the fine print to find that margin of error, right? Or over here, look at that. So 48, 47, that one doesn't have a margin of error. It's because it's a poll of polls. What that means is that they've averaged out all these other different polls, right? Right here, 50% for Romney, and this is the post-ABC tracking poll. So you can see there's the margin of error. So it looks like, oh yeah, Romney totally did better than Obama, but then you realize, oh, wait a second, that's within the margin of error. So this guy's really 47 to 53, and this guy's really 43 to 50, so they technically are overlapping, and maybe they weren't as different or far apart as we thought they were, right? Okay. So I just wanted to show that to you. So when you see margin of error, they're giving you that plus or minus bit over here. And then they'll say, Obama's 50% plus or minus 3%, right? So what you really want to be able to do in your head is make an interval out of that. What they're saying is not quite what it really is, right? It's really more wiggly than they're trying to show you on these things. And this is not just CNN, this would be all of them. They all report this way. They'll say, this percentage, 48%, right? And then they'll give you a margin of error later on. Although, again, they won't do that with that particular one that I'm looking at, because that's poll of polls. Okay? All right, so let's go back here. And we now know how to make those for our own benefit. Good. So a graph of the intervals is drawn below. As it turns out, the proportion in the box was 20%. I just know that because I counted them when I put them in. So you're going to draw a solid line representing that value. So there it is, solid line. Okay. So you can see the intervals. So this was yours. Like you said it was, what was your value? 17.3 to 32.7. So that's this one right here. 17.3 is that low number. 32.7 is the high number. Neighbor number 1 was this one, 22.5 to 39.9. Those are percentages, by the way. I really should put that in there, because otherwise it seems like it's whole numbers. Okay. And then over for this one, that's 11.4 to 25.2. And you could keep going. And as a matter of fact, I do down here. This is another scoop thing. So you keep going and going and going and making interval after interval, but there's some true proportion, and that's what that red line represents down the middle, what it really was for that entire box. All right, so notice that one of those intervals, your neighbor number 1, his interval or her interval does not contain the true proportion. 95% confidence level means that that's going to happen about 5% of the time. 5% of the time, the true proportion is not in that interval. So if you only have just one interval, you don't know whether your interval contains the true P or not. Like if you only have one interval, how do you know if you're one of these ones that has the true proportionate, or if you're this guy that doesn't? And that's why, honestly, they do poll of polls like this. So what the reason they're doing that is they're trying to get rid of that error between interval after interval after interval. So if they take Ohio from one week to the next, it might be up and down and up and down, sort of like it was for our graph. One week Ohio's like this, the next week Ohio's like this, the next week Ohio's like this, and so on. And they do a poll of polls to try to average that all out and find out what it is overall. All right, so suppose that our class had 25 students and each of them gathers data from the bean bin. So how many different intervals will we make? Well, 25, because every single one of them would have its own interval. And in elections, what that is like week to week, especially the presidential election. They'll have, they had one 2 months ago, and then one 7 weeks ago, and then 6 weeks ago, and then 5 weeks ago, and so on and so on and so on. And they just keep going like that. Okay? So what would a graph of that look like? It'd look like this, right? So you have, one interval's there, and the next interval's there, and the next interval's there, and so on and so on and so forth. And everybody's got their own intervals. And then the true proportions, that blue line going down the center. And you might notice there's still one interval in there that didn't have it. That's because we made 95% confidence intervals, which means 5% of the time, 1 out of every 20, you're not going to have it. Which, oops, that was what we found out here. What percentage of the time are you not going to have it? So you take 0.05 times 25, and that's equal to 1.25. So we figure about 1, maybe 2, about 1, maybe 2 intervals won't contain the true proportion. And when you're looking at CNN or Fox News or NPR or whatever, pick a news site. I mean, when they're polling and they're showing these numbers, you don't know which poll it was, right? You don't know if this was, look, they did Ohio here on the 26th of October. They did Ohio on the 29th of October. You don't know whether it's really changing or whether they're just getting different statisticians, they call it the noise, so you get all this kind of up and downness, but that's just natural anyway. So suppose you had one week where, I don't know, Obama was really low or really high. Perhaps that was just a fluke week. Maybe that was the week where it was off a bit, right? It's going to happen about 5% of the time. So if you do this 25 times, you'd expect about 1 to 2 of those times to just be a little bit off. All right, we're done there. I think we should stop. And I'll pick up here next time. Oh, maybe not. I think I could do this. Okay, so let's get through it. So this is the formula for a confidence interval. I honestly put these together all the time. I just say plus or minus when I write it. Okay. Notice that this has to be from a data set in which n times p times 1 minus p is greater than 10, and you have to have n less than or equal to 0.05. Now that should be sounding familiar to you because we ran into that at the very end of chapter 8. All right, so let's see this stuff. When we're working with these proportions, what we're really working with is the binomial distribution. So you have a fixed number of trials, like you're calling this many people. And people's opinions are independent of each other. And again, you can think back to the scoops of the beads, or you can think to calling, people about, the latest election or whatever. But what I believe isn't going to affect what, somebody who I don't even know believes in the same area. I have success and failure. I agree with this position. I'll vote yes on proposal, whatever. Or I'll vote for this candidate, that kind of thing. And failure is you don't agree. I'm not going to. So it's got success and failure. It's got independence, and it's got a fixed number of trials. That is binomial. Now, at the bottom of the box, we said that little n had to be less than 0.05 capital N. Now, we've seen that before. What does that do? The answer is it ensures independence. Remember, you don't want your scoop to be so large that it too greatly affects what's left in the box. That's why we take pretty small scoops. And what we said in section 8.2 was that it had to be less than a roughly 5% of the capital N, which wasn't hard to, we just kind of waved our hands at it like magic for the bead box, but the box was quite large, and so our little scoop really wasn't affecting it very much. Right, but your scoop has to be less than 5%. We also learned what this little formula was, right? We learned that in 8.2. That's the sampling, the standard deviation of the sampling distribution of sample proportions, right, of p-hats. In other words, if you take poll after poll after poll, how far apart should the polls be from each other? Scoop after scoop after scoop, how far apart should the proportions be? That's what this is a measure of. It's a measure of the spread of sample proportion to sample proportion. Now down here, we also learned that n times p times 1 minus p is important. If it's greater than 10, then that shows us that our binomial distribution is approximately normal. And that's good for us because we don't really know how to do things that aren't normal, with the exception of the binomial distribution itself. Right? So we need normal. That way we can use z-scores, right? See the z right there? That's the standard normal score. So you can't use that unless you know it's normal. So the n times p times 1 minus p thing ensures normal. Then the little n less than 0.05 ensures independence. You got to have independence or you can't have all the rest of the stuff. All right, now we'll stop and we'll meet right back here for the margin of error.